For coming to our breakout session about artificial intelligence and security. It is my great pleasure to host today 3 of our leading lights in computer security, and I get to ask them questions around what does it mean to have artificial intelligence and security. And today we're going to focus on 3 framing questions. First question is, what can artificial intelligence learn from security? We are all extremely excited about the potential of AI. We know there are downsides. The security field is one where we've sort of thought about downsides and attacks for a long time. What are some things to consider? What are some things we can learn from that field? The second question is, what does security learn from artificial intelligence? You'll hear today about some surprising new results in computer security powered by the techniques that you may be familiar with from machine learning and other branches of artificial intelligence. And finally, we'll spend a little bit of time talking about what happens after AI succeeds. We do believe that every kind of business process, every kind of part of our lives will be transformed by the different parts of artificial intelligence we're building, as you may have heard in Harry Shum's talk. So looking a little bit further out, assuming this actually works, which we believe it will, what is security going to look like? What will it look like when an algorithm controls who gets jobs, who gets food, and who gets rewarded? And these, of course, are not nearly as theoretical as they sound. I actually heard a very interesting anecdote at the reception the other day. How many people use the website Zillow? How many people check the price of their home on the website Zillow? Everybody. Well, that's a limited form of artificial intelligence. It's trying to figure out how much your home is worth. And they had a change to their algorithm which caused someone's home to lose $50,000 just like that. So we're already living in this world. And it's my pleasure to introduce Dawn Song. Dawn, you could raise your hand. Dawn comes to us from the University of California at Berkeley, where she has done fantastic work in all fields of computer security. Actually, one of my very first papers was with you, Dawn. Tai-Soo Kim comes to us from Georgia Tech. And then Mike Walker, who just joined Microsoft from DARPA. So Dawn, I'd like to turn it over to you to give your perspective on these questions, and then we'll have a discussion with several of the others.
Great, thanks, Dave. Yeah, I'm Dawn Song from UC Berkeley. So this session will cover 3 key questions that Dave just mentioned. Due to time limits, I will mostly focus on the first question, what AI can learn from security, and I'll briefly touch on the 2 other questions. So we're living in this exciting time, and especially for us who have done work in security, there's a lot of really exciting questions at the intersection between AI and security. On one hand, AI can be an enabler for security, and on the other hand, security can be an enabler for AI. And in particular, in this talk, I will focus more on how security can enable better AI, providing stronger integrity, confidentiality, and also preventing misuse of AI. So for AI and security, really it's about AI in the presence of attacker. And it's really important for us to consider AI in the presence of an attacker for a number of reasons. History has shown that the attacker always follows the footsteps of new technology development, or sometimes even leads it. And I think Mike later on will give you even more interesting historical perspective on that. And also this time, the stake is even higher with AI. As AI controls more and more systems, attacker will have higher and higher incentives to attack AI. And also as AI becomes more and more capable, the consequences of misuse by attacker will also become more and more severe. And when we look at AI in the presence of attacker, essentially there are 2 categories, 2 prospects that we need to pay attention to. One is how the attacker can attack AI by, for example, causing the learning system to not to produce the intended and correct results, or even more so, causing the learning system to produce targeted outcome designed by the attacker. And they can cause the AI system to leak sensitive information about individuals. And to address these problems, we need better security in the learning systems. And the other aspect is the attacker can try to misuse AI to attack other systems. And in this case, we actually need to solve an even harder problem, not only just to improve security for the learning systems, but also at the same time, we need to actually provide stronger security in other systems. And again, in this talk, I will mostly focus on the first part, and in particular, what we can do about securing the AI systems, or what kind of problems can arise when the attacker tries to attack AI, and what can we do about it. So probably a lot of you have seen this. On one hand, deep learning systems have been making amazing advances, such as AlphaGo and reaching human-level performance on ImageNet dataset and so on. But on the other hand, unfortunately, deep learning systems are very, very easily fooled. So in this example, on the left-hand side, these are the original images, which are correctly classified by a neural network-based image classifier. And the middle columns are what's called adversarial perturbations. So, and here, these are magnified so you can see them. Otherwise, they're really, really small. To human eyes, you can barely see them. And the right-hand columns, these are called adversarial examples. What they are they are the original images with the adversarial perturbations added. As you can see here, to human eyes, you can barely see the differences between the original images and the adversarial examples. But to the image classifiers, essentially these adversarial examples, they actually cause the classifiers to misclassify. And we have done a lot of investigation in the area of adversarial examples. As it turns out, besides just image classification tasks, actually adversarial examples are really prevalent in deep learning systems. For example, we've looked at other tasks and model classes for generative models, deep reinforcement learning, and so on. And also we've looked at these attacks actually be effective even when the target model is not known. So previous work mostly focused on when the target model is known. You know the architecture, you know the weights. But our work also showed that even in the much weaker systems where the target model is unknown, such attacks can be very effective. So here, I'll just very quickly show you some examples. The first example is the generative models. In generative models, you have inputs that goes through an encoder stage that produces the latent vector, which goes through the decoder stage where the original input is trying to reconstruct the original input. And these generative models are very useful for lots of different applications. And one of the applications is image compression. And the recent work has shown that neural network-based image compression has reached state-of-the-art. And here we can consider an attack scenario. For example, a lot of the security surveillance cameras, what they do is that they actually record the images, and then they compress it, and then they throw away the original images, only store the compressed versions. And later on, when the law enforcement comes back to investigate a crime scene, they will try to decompress the stored compressed images, try to reconstruct the original crime scene. So here we look at an attack scenario where the attacker tries to generate some essentially adversarial perturbation of the original images. Here it's a 7. By adding some adversarial perturbation, it generates an adversarial example. And then once it goes through the compression stage and then goes through the decompression stage, as you can see, the decompression stage tries to reconstruct the original inputs, but unfortunately here it will reconstruct into something completely different. Instead of a 7, reconstruct into an 8. And you can see the consequences of this if this actually has been used in this security surveillance camera example that I mentioned. So here let's look at some actual examples of how vulnerable these generative models can be. Here's an example where these are the original images from the ominous handwriting digit dataset, the standard dataset. And this is a reconstruction of the original images using a generative model. And as you can see, these reconstructions of the original images work fairly well. But now let's say that the attacker wants to generate adversarial example versions of these original images so that after the encoding and decoding stage, it will actually generate into something like this tag image in 0. So here are the examples of the adversarial examples version of the original images. And here are the reconstruction of the adversarial examples. As you can see, they're all turned into something like this tag image. And this is the street view data. Similarly, as you can see, this adversarial example version of the original image gets turned into something similar to the tag image. And here's for the face data set, where again, the adversarial examples of the original version now during reconstruction gets turned into the something very close to the target image. So that's an example of generative models. Here is another example that we've looked at in the deep reinforcement learning setting. So deep reinforcement learning is very popular these days. For example, AlphaGo actually uses some of these techniques. And here's an example of a deep reinforcement learning trained agent playing the video game Pong. As you can see here, it actually plays fairly well. And in this case, actually, it trains to play to the max reward. But here we want to look at what happens when the attacker tries to attack this learned agent. So for this agent, what it does is that it takes the input as the input video frame, and then the neural networks essentially is the policy that will try to, given the input frame, it will try to predict the action. So then what's for the attack here, essentially the attacker is trying to add this adversarial perturbation to the input frame, and then essentially try to fool the learned agent. And what we see here is that the attacker actually is very successful. They can generate, can insert a very, very small adversarial perturbation so that the learned agents, then the same agent which has been very successful early on, that reaches the max reward 20. Now, after the adversarial perturbation has been injected into the input frame, now the same learned agent completely fails the task and reaches the minimum reward, negative 20. And also, we looked at even smarter attacker strategies where the attacker used the learned value function to try to guide the attack to figure out when it needs to insert the adversarial perturbations. So it doesn't need to insert in every video frame. It only needs to insert in a very small fraction of the video frames, where it still makes the attack successful. Essentially, the value function is an estimator about how much rewards that the agent may get at that state. So here's an example. This is the original input frame, how the agent behaves, like what you saw earlier. And these are the examples where, as you can see to human eyes, these videos look exactly the same because the adversarial perturbation generated was so small. After quantization, actually, they are identical. And then in this case, the middle column is when we add the adversarial perturbation on every frame, and as you can see, that the attack completely fails. And then the right-hand side column is when we only inject the adversarial perturbation guided by the value function in a very small fraction of the video frames, and also, as you can see, the agent completely fails. So again, so these are just examples showing that the adversarial examples are really prevalent in deep learning systems. And also, the whole community has been investigating a lot of defenses. I had to remove the slides because there is not enough time. But the short answer here is that there actually has been over like 60, 70 papers written just in the last 2 years proposing various different types of defenses against these attacks. And today, we still don't have a good solution. And so far, I've only talked about adversarial examples fooling learning system at the inference time. This is also called evasion attacks. The attacker can also fool the learning system at the training time. That's called the data poisoning attack. And the Microsoft's Twitter bot example can be seen as an example of the data poisoning attack. And all these essentially are in the area of adversarial machine learning. It's about how machine learning in the presence of adversaries. And this adversarial machine learning is particularly important for security critical systems. So I strongly believe that security will be one of the biggest challenges in deploying AI. And this really motivates us to figure out how we can improve the security of the learning system. And there are many challenges for security of the learning system and at different levels, in particular at the software level, learning level, and distributed level. So at the software level, the goal is that we want to ensure that there's no software vulnerabilities such as buffer overflows and access control issues, where it will enable the attacker to take control over the learning system through exploiting software vulnerabilities. So luckily, this is an area that we are very familiar with, even though there are still lots of open challenges. But the existing techniques that we have developed over the past decades, existing software security formal verification techniques will apply. And these are just some examples of actually my personal work over the last 20 decades, taking different approaches, defensive, reactive defenses, bug finding, and secure bug construction. All these approaches for solving software security problems. And all these techniques essentially apply to security for learning systems at the software level. So I would say that the bigger open challenges for security of learning systems is at the learning level. And there are a number of different challenges in this area. Again, due to time limit, I will only give you a few examples. The first one, this is an example that we can learn from software security domain as well, is that how should we evaluate these learning systems? And it's really important for security to evaluate this learning system under adversary events, not just normal events. And this actually is a slide that I use in my undergrad security class that I teach and stress to every one of my students in my class. It's about the difference between regression testing versus secure testing for software systems. And the difference is that for regression testing, that's a typical just software testing. We run this program on normal inputs with the goal to prevent normal users from encountering errors. Whereas for security, to evaluate the security of a software system, it's not sufficient to just do regression testing. It's really important to do security testing. And by security testing, we mean that we actually need to run program on abnormal adversarial inputs, and the goal is to prevent attackers from finding these exploitable errors before us. And similarly, for learning systems, we also need to make the distinction between regression testing and security testing. Regression testing is, and also this can be done at training and testing stages. So regression testing is basically what every single machine learning paper does today, is that we test on normal inputs, and also in particular, we even want the test data distribution should be similar to the training data distribution, and we try to, the goal is to estimate generalization error. But however, for evaluating the security of the learning system, it's not sufficient to just do regression testing. We actually need to do security testing. And again here, the security testing is that we need to test the security of the learning system on abnormal adversary inputs, similar to the adversary examples that I mentioned earlier, and with the goal to estimate the resiliency against adversary inputs. So that's one challenge. Another challenge is that we actually need to be able to reason about complex non-symbolic programs. As a whole community, we have decades of experience on reasoning about symbolic programs. And for most of us, we are actually, so far, we have been very familiar with the symbolic programs. These are like operating systems, file systems, and so on. And their semantics are defined by logic. And again, we've had decades of experience and developed techniques and tools for logic and symbolic reasoning, including theorem provers, SMT solvers, and so on. And in fact, I would say that we have entered an era of formally verified systems. So these are just a few examples where we have formally verified these microkernels, operating systems, and so on, with formally proven guarantees of certain correctness and security properties. And due to powerful formal verification tools and dedicated teams dedicated to these tasks. Even though in this domain we still have a lot of challenges, but at least we've had decades of experiences and techniques and tools developed. However, the bigger challenges is really in the domain of non-symbolic programs, like the deep learning systems that we are using today. Here, we really have a lot and lots of open questions and challenges that as a whole community, we have very, very little experience with. For example, for these learning systems, for these non-symbolic programs, we have no precisely specified properties and goals. How do you precisely specify if your goal is not to hit a pedestrian for the self-driving cars? How do you even specify what is a pedestrian? And also, we have no good understanding of how learning systems work. And unfortunately, the traditional symbolic reasoning techniques really at this level mostly do not apply. Furthermore, we also have challenges in how we can design new architectures and approaches with a stronger generalization and security guarantees. This is also a huge open challenges. For example, the previous session is on provable learning algorithms and provable guarantees for learning algorithms and so on. So I'll just briefly give an example of our recent work in a very limited domain. as a first step towards this direction. This domain is in neural programming synthesis, where essentially we train neural networks to try to learn certain programming tasks, such as addition, sorting, and so on. And there has been a long line of work in this domain, including work from Google and DeepMind, and so on. And unfortunately, previous work, they all suffer from main two challenges. One is that these neural architectures that learn programs do not, currently the neural programs do not generalize well. If you learn how to do addition with, for 30-digit numbers, they won't generalize to know how to do addition for 60-digit numbers. And the other challenge is that even if empirically the learned neural programs succeed in all the tests, but still there's no provable guarantees that they have actually perfect generalization for the learned programs. Like even if you've seen that they do correctly addition for up to 30-digit numbers, you don't know how they will behave for 31-digit numbers. So in our work, making neural programming architectures generalized by recursion, we propose a new approach using recursion to introduce recursion to neural programs and learn recursive neural programs. Using recursion, essentially, we can a problem is reduced to subproblems, finally into its base cases using reduction rules. So our work won the Best Paper Awards at ICRR. I cleared the top deep learning conference this year. And essentially, with this approach, that we showed that for the first time, that we can actually provide the proof of generalization for these learned neural programs, and also using this approach, I can generalize much, much faster. And this, so from this work, we show that the program architectures actually is really important for provability. And this is also something that we have learned from the traditional software systems. This is, we learned that well-designed programs with good architectures, they're easier to prove properties of, whereas arbitrary programs, bad code, such as bad code, are actually very difficult to prove properties of. And hence, going forward, I think even for neural networks, deep learning, and so on, we want to consider recursive and modular neural architectures, which are easier to reason, prove, and generalize. And also, the more open question is that for more general tasks, what can we do? What kind of new architectures and approaches that we can develop to enable strong generalization and security properties for these broader tasks? And really the key question is, can we have provable guarantees of generalization and security properties for these learning systems? And also another challenge is how we can reason about how to compose components. As we build large and complex systems, it really requires compositional reasoning, where each component can provide abstractions, and hierarchical compositional reasoning can prove properties of the whole system. And then a key question is, how can we do abstraction composition reasoning for non-symbolic programs? And again, these are just a few examples. So the list is actually very, very long. Lots of really open questions at the learning level. And also, there are lots of open questions at the distributed level as well. At the distributed level, each agent makes local decisions. So how can we make sure that good local decisions can achieve good global decisions? So these are just some examples of how security can learn from, how AI can learn from security, essentially how security can enable better AI. And also, on the flip side, AI can enable better security applications as well. Face recognition actually is actually a great example being used in security applications. And then there are other security applications, including using deep learning for better vulnerability detection. Some of the work actually has been done at Microsoft. And fraud detection is a great application for machine learning and deep learning in security applications. And also, recently we've done some work using deep learning for analyzing program binaries for similarity detection for vulnerability detection as well. And one key question, I think, when we think about applying machine learning to security applications is where is machine learning applicable in security applications? So, for example, the examples I mentioned, like the software vulnerabilities, at the software level, these software vulnerabilities, oftentimes we've had a lot of program verification, program analysis techniques developed for that. And the time is really short. I don't have time to go into the details. So there's questions, whether those kind of applications actually are good whether machine learning can do better there. But however, I would say machine learning is really most needed when there's no precise formal property and specifications. Because for software vulnerabilities such as memory safety vulnerabilities and so on, there's precise formal definitions. But for a lot of the other security problems that we constantly face, like spam, fraud detection, compromise detection, detecting bots versus humans, there's no precise formal specification for these problems. And hence, actually, for these problems, machine learning is the only solution we have today for these type of security issues. Right. And then, so this is how, at the intersection between AI and security, what I wanted to end on is, like what Dave mentioned, the last question is what happens to security as AI becomes stronger and stronger. So I think a really important question for all of us to think about is that as AI becomes stronger and stronger, we really need to think about how attacker could actually misuse AI and how we need to improve security in the other systems. The attacker could misuse AI in many different ways. For example, again, already we have seen deep learning empowered bug finding, and also deep learning can enable better phishing attacks using information from social networks and so on. And also, some of you may have seen that misuse AI can be used for large-scale automated targeted manipulation. For example, there's an example from Cambridge Analytica, which has been essentially has helped in Trump's election. And I'll just briefly mention some of the work that we did a while back, showing that in the area, this the consumer-grade BCI devices have become more and more popular, and they are fairly cheap. And they are used for lots of different applications. For example, people use it for better study, playing games, and so on. And actually, there's a third-party app market for these BCI devices. And just like your app markets, there's a third-party app markets for this as well. So the question that we looked at is, what if an EEG gaming app is malicious? What can it do? Can it actually secretly read your mind? So we did some study in this space where the BCI, to see whether the BCI actually can be used as a side channel to the brain, where we showed that by a malicious attacker, by specifically crafting the app to provide certain stimuli to the user and then getting the EEG signal back, the attacker actually could learn sensitive information about the user, such as who the user knows, where the user lives, and what kind of banks the user uses, and so on. So the key point here is that the more powerful these consumer-grade BCI devices get, and also the more powerful the AI technology gets, also at the same time, the more powerful the attacks gets as well, because the attacker gets to use exactly the same technology that is designed to help humans to also launch their attacks. So with this, I think one really important message for the whole community is that with great power really comes with great responsibility. And also, I want to briefly mention another example from the medical device security. Is that we did the first medical device security analysis in the public literature, showed that a lot of these medical devices also have severe software vulnerabilities. And as a result, and also with other researchers' follow-up work, FDA then, in the beginning, initially, for example, at the time of this work, FDA's guidance for medical device approval had no mention of security. And last year, FDA finally issued guidance recommendation on medical device security. And similarly for AI systems, we are still at a very early stage. There's no policy, there's no regulation. So again, as I mentioned, I strongly believe that security will be one of the biggest challenges in deploying AI. And it's really important to consider security for AI from very early on. And secure AI is important and necessary for future advancements of AI. And also, secure AI is an interdisciplinary community effort, for example, requiring even policy and legal help as well. And there are lots and lots of open questions for the future of AI and security, how to better understand what security means for AI and learning systems, how to detect when a learning system has been fooled and compromised, how to build more resilient systems with stronger guarantees, how to mitigate misuse of AI, and what should be the right policy to ensure secure AI. And let's tackle the big challenges together. Thank you.
Can I get the clicker? Okay, let me start by introducing myself. I'm Jim, currently an assistant professor at Georgia Tech, but before that I recently got a PhD from MIT. My general research interest in systems, in operating systems in particular, and system security in general. The thing about, in terms of security, my career as a security researcher started about, like, I'll say 12 years ago when I was working as a security agent in South Korea. And in terms of AI, I have an interesting background. In fact, I admitted as a machine learning PhD at MIT, but I changed it to security at the very first day, which turns out to be the worst mistake that I made, according to these phones. But in other words, I have a little bit shallow idea of what is AI, but I'm confident about the security, so let me talk about that a little bit more detail. So before we jump into the topic between security and AI, let me clarify a little bit. Because the term is ambiguous, AI is ambiguous, both security and AI even worse. So here, the security is basically software and computer security. In particular, I'm going to talk a little bit about attacker's perspective, not the security in general. In other words, I'm going to exclude any security-related issue that requires some human involvement, like fraud and phishing. These are extremely good applications for AI, but for the discussion, I'm going to exclude that. In terms of AI, instead of talking about AI itself, I'm going to talk about the mechanism, like machine learning and deep learning in particular. So anything, the train-based approach, sometimes their behavior is just stochastic, for instance. These are all work well in practice, but sometimes they're too complex to understand why they're working. So I'm going to talk about these in more detail. So for the purpose of discussion, I'm going to make 3 points. So what AI can learn from security, what particularly important thing about security is a thing as an adversary, we typically call threat model. And this kind of practice is really important because most of the machine learning approach is talk about stochastic results. So in security, if you say like, we achieve 99.9% of accuracy in your system, it's still insecure because there's a 0.1% of insecure component in your system. So secondly, so what security can learn from AI? One thing I really like about AI is their approach to measure and quantify the progress of research. Sometimes there can be a lot of interesting events like AlphaGo and chess, which even people outside of computer science can understand what's going on, and they're a great achievement of AI. The last part, what if AI takes off? Actually make me a little bit worried because it opens a lot of opportunity for attackers. So I'm going to talk about what are the potential attacks that we have to worry about when AI takes off in our world. So how many people have a Tesla here? Wow, interestingly. Okay, there's one. So can you steal or hijack his Tesla? What is the best way to hijack them? What? Oh, yeah, that's the easiest one. And still the threat? Oh yeah, hotspot is one good thing. So typical approach, like you mentioned, is a physical threat. We put a wall in front of Tesla so we can stop it and hijack them. Much easier, and we can make it a little bit intelligent. We can spoof the sensor. Probably we can target it to the sensor of the Tesla by using this laser or acoustic signals. The impact of this kind of approach is really larger than physical attack because we can launch the attack remotely. We can even go further. What if we can fool the algorithms itself? We can put the stop sign, but they're contradicting each other. So how can you decide? It's probably they fall into the safe mode, try to stop. That's an easy way to hijack. But do you know how adversary actually think about this problem? The very interesting way. They actually put the circle around the Tesla. They can trap them. You know, when someone, as a software engineer who think about this self-driving, who developing self-driving car, how many people think about this kind of assumption? There's so many corner cases you never think about before, but Adversary has the opportunity to tackle the problem. So once they find out this one weakest point of your system, they can compromise your system. So who are the strongest adversary? Let me introduce this guy called Loki Har. He's one of the best hacker in our generation, arguably, and he did like full chain exploitation of all major browsers and platforms. He actually claimed more than millions of dollars in total last 3 years, including this phone-to-own and PhoneFast. So the Google has to pay so much money to him. He recently hired in Google Project Team Zero. I had a good chance to meet with him in this closed conference among the high-profile bug bounty hunter. And a lot of people is really wondering about what he's actually doing. What are the general approach to find the vulnerability? So one cloud asked, hey, could you explain how you actually found the vulnerability in this specific the competition? He said, because he never speak English, so his friend actually translated his English for him. But what the interesting word he actually said to all of them is intuition. In fact, that's a very surprising fact, but except there's one bug that he had to open the IDA, this is reverse engineering tools, and just confirm that his intuition is correct. So if you see his exploitation, unlike the normal people, he actually wrote the 1 or 2 line to bypass all the way from the browsers and kernels and hypervisors and launch the remote attacks. So this actually gives a very interesting observation in security. So when we are dealing with the security issue, particularly exploitation writing and penetrating into the systems, when you're designing a software defense mechanism, we try too hard to translate our intuition into the methodology. So hope is that we can expand this kind of search beyond a particular instance of software. But on the other hand, what's interesting here at machine learning in particular is we are trying to infer some of the intuition that we have by putting a lot of data. So hopefully we can get a nice parameters and weights and nice feature, for instance. So what's interesting is if this mechanism do not work out, then what they typically do is they blame the data, the quality of data. Hey, let's collect more data. And this kind of interesting practice in machine learning is quite the opposite of the security. So actually even worse than, not many security practices do not have much data. For example, we are dealing with the 0-day vulnerability by definition. It's not known to public. But how could you find those kind of vulnerability and high-profile vulnerability by using this approach? So I want to make this message to you guys. So it's really important to remember that attackers really target a single weakest point of entire systems. If you talk about 999%, it's still not enough as a defense mechanism by using AI. So we really need to think about the assumption that we have. Even we typically call threat model when you're designing, particularly when you're applying AI to the security. So sometimes people say, hey, you're not capturing intuition because we are lacking the number of features. But why not just increasing number of features? But in fact, this is actually increase the attack surface to your system and likely to give a good opportunity for attacker to bypass, not only just bypass and penetrate into your systems. So we, in security and machine learning community, we really need a better way to directly translate our intuition to the model and features in more intuitive way. So another important thing that I want to say is that something didn't happen. We need a better, I would say, comprehensive way to iterate this process so we can enhance the model. Let's talk about the second question. What security can learn from AI? One thing I really like about AI is there are a sequence of events that we can understand very easily, starting from 9050, like tuning test and chess competitions and self-driving car by DARPA, and recently Jeopardy and Go even like last year. But actually, the community took off even further. In the Electronic Frontier Foundation, they recently announced this community-driven effort to quantify and measure the progress of AI in all together. So what they're proposing is that they have a common set of data set. So once you publish the paper, they're gonna extract the core algorithm and put it all together if you evaluate in this automatic way. So once you announce the algorithm, in every single subfield, they're going to provide this nice, pretty figure so that someone who wants to use those mechanisms, they can compare pros and cons of those algorithms. Said that, then what happened to security, and particularly privacy as well? Probably the problem is the security itself is too subjective. The notion of the security is really depend on the context that we are talking. And in most situations, we don't even know what we mean by measuring security. Typically, security is binary decisions. Is secure or insecure? But sometimes the secure system can be insecure once we found some zero-day vulnerability outside. So most of the notion with the machine learning and many stochastic approaches is not quite well aligned with the security in general. So said that, we have a lot of interesting competition out there, like among CTF, we captured the flag competition that really the top hacker compete head-to-head each other. And we also had a kind of interesting event that the computer, instead of instead of actually human typing something, that we can just watch how the computer is play each other. But in fact, I believe this is still infant stage, that we are, it's not like compatible to what human doing in whatsoever. So one take-home message from AI is that AI fields drive their research in various landmark competitions, which easily approachable, which is quite approachable by common people outside of computer science. So in community, they strive to collect the public resource for quantifying their progress in research by sharing their data set, etc. But what's interesting in security is that a lot of people don't want to share their data because say, hey, I have a security instance by company, it's kind of a shame for them. And a lot of people consider that as one of the confidential events internally. And of course, admittedly, security is very subjective. But what if we can tackle the subfields of the security so that we can, at least some part of the security can be quantified in various ways? In last question, what if AI takes off? What are the potential security issues? Again, if I'm taking machine learning, if I remember when I'm taking machine learning class, many of my colleagues say, hey, in this homework, it works, but I don't know why it actually works. It sounds like magic. Right? This kind of trend and like feeling, it should make me very scared. Because in other words, a lot of people, the AI is everywhere in your software stack, including your firewalls, intrusion detection systems, which means basically so many unknown software everywhere. In particular, if you really worry about the APT attack, which is called Advanced Persistent Threat, it's basically not the normal attack launched by script kiddie, but the attack that actually targeted specific people. Often is backed by government and states and some large organization, etc., like Stuxnet. In fact, if such unknown software is everywhere, isn't it really making such penetration easier? Is a good question we have to think about. So one take-home message from this question is that in the future, if we have AI everywhere, basically now, previously we have to just worry about the implementation of particular software, but now we have to worry about implementations, algorithms, and data sets, and their training set as well. There's so much attack surface you can easily penetrate into. And most of the time, the programmer do not understand what they're doing, but attackers sometimes have a more deep knowledge about how system works. And if that's the case, once attacker penetrate to your system, but it's really hard to detect even because we don't even understand what's going on. So in the future, probably accountability is one of the most important things that we need to have. As part of this research effort, we're going to present a project called AV Pass in Black Hat this coming month. It's basically, given a malware, we're going to keep interacting with the antivirus software and manipulate that, then essentially bypass this AV software outside without knowing anything about the antivirus software. It turns out to be pretty easy. Let me finish my talk by introducing two ongoing efforts at Georgia Tech. It's just not my project. It's interdisciplinary work between security peoples and machine learning. So it's quite similar to what Don was explaining to us. It's basically about adversarial machine learning, but in the context of antivirus software. So we want to apply machine learning-based approach to identify the malware. So another project it is supported by Intel, but another project is ongoing work as well, is supported by NSF. We want to even generalize this approach even beyond the malware. So can we really find out an interesting and resilient machine learning algorithm that's applicable for more broader applications as well?
Thanks, Tyson. My name is Mike Walker. I recently joined Microsoft Research from DARPA, where I ran Cyber Grand Challenge, the AI versus AI computer security competition that both my fellow panelists competed in. For those of you in the room who are computer security professionals, I'm going to talk a little bit about the history of the computer security industry, just to answer our framing question, what can AI learn from security? But for those of you who are joining this talk directly from working on AI, who haven't maybe studied historical lessons from the computer security industry, some of this may be relevant or useful to you. So 1996, we saw Smashing the Stack for Fun and Profit, this first public description of how to use very simple buffer overflow attacks to take over remote programs on remote servers. And the temptation in 1996, when this was first described, was to say, well, now that we understand it, we can prevent this. Fast forward to 2011, when cybercrime was a $114 billion problem for the global economy. This breakdown by Trail of Bits was an attempt to look at every single major break-in into business and root cause what allowed the intrusion to happen down to the flaws and then count them. And it turns out that the vast preponderance of flaws used to enable cybercrime well over a decade after this was published were memory corruption flaws like stack overflows. So I think that the teaching moment for AI is when we see these first publications. It is possible to generate adversarial counterexamples, and they work even when they're printed on a piece of paper. Or it's possible to poison training data sets, is to take these threats seriously and to understand that it's not enough simply to understand the threat, but also to begin working not just on how to prevent them as we deploy AI systems, but how to get the knowledge about how to prevent them out there. This is the slide from Sandy Clark's paper, The Honeymoon Effect, where the research was done to look at software flaws versus security issues. And over a really large set of software, the key takeaway here is that we kind of understand how bugs work in systems. During development, we identify bugs, we drive bugs to zero, we ship. But security flaws don't follow that intuitive pattern where we drive them to zero. They actually happen later. And there's this period after a new piece of software is shipped called the honeymoon, where there are no security flaws. Somewhere around 100 days on average, but sometimes it can last for years. But once there is attacker adaptation to a new system, security flaws take off. And this actually leads to kind of an incorrect selection bias where we believe that newer software is more secure because it hasn't been attacked yet. And older software that is in the middle of the runaway ramp of the honeymoon effect seems insecure, whereas it is actually not. And I'd like folks working in the AI field to consider that we may be in a honeymoon right now, where we aren't seeing active attacks or even reports of active attacks, but that does not mean that they're not in our future. On the topic of no reports of attacks, this is one of the slides from Mandiant's APT1 report, which came out in the early 2000s. And Mandiant was a company that was formed around going in and doing breach investigations in major companies. In this slide, they've placed a yellow dot every time they did a breach investigation in an economic sector. And each one of those yellow dots is a breach into a company that was running modern security software, that mostly had good patch compliance, and that was defeated by an intelligent adversary that was working to steal information over time. The thing to realize about this slide is that when this report was published in 2012, 2013, then we had reports of cyber attacks. But for 6 years, there was silence. And that silence kind of comes from the prisoner's dilemma, where no one wants to be the first to speak out. So I would encourage everyone to say that maybe we don't have a report of active poisoning of an AI system in production, but please do not mistake a lack of reporting for a lack of a problem. And the key here was the development of a threat intelligence industry where companies that were affected by these sorts of attacks shared information with each other about threats. So the time to build a threat intelligence industry for AI is now, before this happens. If you are seeing attacks on your production system, if you are seeing that smoke, guaranteed you are not alone. So there's some golden opportunities now in AI and security. In general, any software that's going to serve as a gatekeeper to value will eventually see the introduction of an expert adversary, the advanced persistent threat, someone who is studying that software and learning how to defeat it. And just as much effort will be put into defeating it as stealth. Attackers that break systems for profit always put enormous effort into non-detection, hence the APT1 slide. Attack detection isn't free. If we read no reports of attacks on AI systems, that can be an artifact of no attacks, or it can be an artifact of the fact that we are not studying for attacks. We haven't built the sensors, and we haven't built the threat intelligence yet. And the threat intelligence industry took a long time to build in the computer security arena. And finally, techniques to defeat AI systems will be discovered, but we get to choose how they're discovered. If they are discovered in the open and they are published, then we can start working on mitigations. And hopefully we can have a much shorter timeline than some of the initial timelines in the computer security industry. So that's my close for what the AI field can learn from the history of the computer security industry. What can the security industry learn from AI? Quite a bit. I think that when we think about encryption, it's a field where we can predict how much work our opponent has to do to decrypt our data. But there's a whole bunch of cycles in the computer security industry where we're reliant on predicting how much work an adversary has to do to defeat us. So one example is the malware sandbox industry. The way that we learn about malware right now is we get feature identification through dynamic analysis by running malware inside an instrumented sandbox, an imitation computer. It turns out that Sandprint, paper out of RAID in 2016, shows that you can use machine learning to accelerate the process of detecting sandboxes. As a matter of fact, Sandprint was able to achieve a classifier with 100% accuracy for every malware sandbox that they could download, and 100% accuracy on anything that they could test on the internet, even without access to source code. And because it's driven by AI, it's repeatable. That's constant stealth evasion over time. So the security industry's assumption of how much work we have to do to get good feature extraction out of malware has been defeated by an AI system. And that may continue to happen to other assumptions that the computer security industry is making now. This is a fuzzer called AFL. It's published by Google. And if you have a computer on your desktop, I guarantee you that some critical software inside that computer has had a security bug discovered in it by AFL. AFL has a page called its trophy case where it just lists software where it's found a critical security flaw, and it is enormous. AFL is one of the absolute best security testing tools for unknown software flaws. And this is a progression of images that it created with no a priori knowledge, just by studying traces of how a JPEG library worked. And you can see it kind of creating valid images that will render in a browser. The surprising thing about this is that there are no neural networks involved. There's no machine learning technique. This is simply done through tracing and feedback. So there is an enormous opportunity here for adversarial systems that learn about flaws in software to have a meeting of minds with the AI field. I think it's already been said by my fellow panelists that the ability to find exploitable bugs in software right now is an adversarial contest of the mind where automated systems are still in their infancy and are not competitive with human beings. We can see the the successes in contests like chess and Go, but for this contest, there's enormous opportunity for new research. Security and AI in the future. I have to talk about Cyber Grand Challenge. Brief review, this was a contest between automated systems. These automated systems were placed behind an air gap. They did 10 hours of compute, and they were all given the same previously unexamined software where they had to play an adversarial game, find and exploit flaws in their opponent's software, defend against use of those flaws in their own software. And it's worth noting that the kind of the core technology stack, automated binary program analysis, one of the luminaries of the field is up here with us, but that's Don's system, Galactica, on the far left. And I'll tell you one anecdote that happened during this competition, somewhere in the middle, around round 50. And by the way, this is all public data. There's an open corpus of every event that happened during the contest, so you can go back and replay it. But Galactica discovered a new flaw in software. It wrote an exploit for that flaw. It smashed the stack for fun, not for profit, and landed a successful Stack Overflow attack against all of its opponents. And the next round, which was 5 minutes later, the red system, Deep Red, fielded a protected stack version of its code. So it had changed all of the stack data structures to non-executable using a stack pivot, deployed the automatic patch. But in the next round, Galactica exploited that patched version by using what's known as a ROP attack. And it was an adaptation just to that defense. It was unique, didn't use that attack against any other system. And Deep Red saw the adaptation of the attacker system and responded by fielding an IDS rule to prevent use a specific memory address, basically blacklisted that memory address on the wire, and Galactica adapted again and started attacking a different flaw, unsuccessfully that time. And Deep Red actually managed to, through adversarial cycles of counter-adaptation, actually stop an attack while it was happening. And I think that automated systems engaged in adversarial cycles inside the reaction speed of humans was kind of first witnessed inside this prototyping competition, but we have to expect that it's coming to the real world. And while that does sound a little bit scary, I would like to say that computer security as a field has been dominated by the structural disadvantages of human beings doing defense. Human beings cannot react to attacks as quickly as they happen because they can't do the reasoning quickly, and they cannot look at the scale of data that our networks actually create. But with machines, those structural disadvantages of speed and scale are gone. And what you get when you get an attacker-defender contest between AI is you get the superior system wins. And hopefully, the superior system in the future is going to be the system that is better engineered. And we're going to have an opportunity to kind of upset this balance of power that's been so dominated by attack for so long. So I think with that, I'm going to hand this over to David.
All right, thanks very much, everyone. Thank you, Mike. We're going to come and have a little bit of a panel discussion here. We'll have some structured discussion on each of these points, and then we'll end a little bit early, so if anyone wants to have questions or can meet with the panelists, you'll have that opportunity. The only thing is that Mike will have to leave a little bit early, so please come on down. And so I want to start off by reviewing the pieces around what can AI learn from security. And I actually want to hark back to what we as a security field have done when we've discovered that people are poisoning our training sets. I mean, Dawn, you had, I think the first paper I'm aware of that talked about poisoning training sets a decade ago. Would you like to talk a little bit about that and how people reacted to that in the security industry?
Sure, yeah, thanks. And so, yeah, so David is referring to, actually, some of the things in my talk that I only briefly mentioned. I didn't have time to go into details. Actually, it's a great example also showing where machine learning should be used in security applications. So this is an example where we are dealing with worm attacks. So recently, actually, we've seen some of the very recent worm attacks where now it's actually as a ransomware attack. But essentially, in a worm attack, the attacker exploits vulnerabilities in software, and then take control over the compromised host, and then it self-propagates. So once the host is compromised, then we'll very quickly go try to attack other vulnerable hosts, and hence these worm attacks can happen really, really fast. So some of the examples in the past, at the peak time, actually the attack can compromise over like thousands of machines per second. That's how fast it is. And then naturally we want to develop defenses. Ideally, we want them to work in real time and so on. So then one way to do that is by trying to generate worm signatures to detect these worm attacks, and hence you can block these worm attacks. Then this actually can be viewed as a learning problem where you have labeled examples where you have these exploits, worm attacks. So you have essentially these bit sequences that are labeled as worms, and also you have normal traffic, then essentially these are labeled as non-attack. And then the goal is to learn a classifier to then given a packet or sequence of bits to determine whether it's a worm attack that you should block or it's a normal traffic that you should let through. And then in here, as you can see, so also the interesting thing is that here actually the attacker also has control of showing what, in some sense, like what examples you see and so on. So then also as you learn the classifier, the attacker actually has an interaction with the classifier as the attacker sees that if its attack is being blocked, it can actually change, morph its attack and try to make the classifier ineffective. So as you can see, this actually is an interactive game. And in this case, then essentially the training data, the labels, as you can see, they actually could be poisoned. And we actually studied the various settings where the classifier can actually learn the wrong model. And also, as you can see, in this example, it's actually really expensive for the classifier to learn the wrong model because time is at essence. If the classifier learns the wrong model, and then it gives the attacker more time to propagate, to compromise other machines. And so the more iterations that it takes the classifier, the learner to learn the right classifier, then essentially the less chance of actually being able to protect the vulnerable hosts. And in some of our work, we actually gave some lower bounds in the impossible of some of the hardness results in this type of interactive game to actually use it to learn the.
So that seems like a case where an example of the honeymoon effect you were talking about, Mike. So what I'm curious about, Mike, is let's suppose you were given operational responsibility for one of these systems that Dawn's techniques are going after. What would you do to look for this stuff?
So I think it was Sergi Broadus who said that defense is the child of offense, and you can see this in the way we name mitigations. You know, Stack Overflow defenses are named after the attack they prevent. So I think that open publication of attack research, like Dawn's doing, has to be immediately followed by detection and mitigation work. So anyone who is running a machine learning-based system that is acquiring untrusted data from the outside that's going to be used to train needs to be searching for these attacks and using the open publication of data or the open publication of techniques to train their detection and attack team prototyping, like red teaming, to make sure that that detection is working.
Yeah, and Taisu, I really liked your point about security. We're trying to codify intuitions, right? And especially your point was like that's almost sort of like learning from data and trying to turn that into classifiers.
Right.
If you think about like the intuitions we need in order to detect these kinds of attacks and create the accountability you were asking for, like what do you think would that look like in today's world?
That's a pretty good question, but in other words, hard to answer in general. But accountability argument is that once something happens, for example, my machine learning base, the detection system is not working, but we need some clue about why it's not working, so that I can actually come back to the systems. Either you implement again, or we need more different set of data that can cover it. But we don't know what to do next, other than naively increasing number of the data potentially you can train with for the new model. I think one thing that's very interesting thing about machine learning approach is that people start with the feature engineering, which is kind of a way to encode the intuition to the machine learning-based algorithms. But we need a more direct way to represent this one, other than this feature engineering that we are doing.
And I like the point about feature engineering because it actually reminds me of Dawn, I thought really interesting about your work on adversarial learning. The fact that you had the epsilon 0.005 and you can completely screw up the Pong player. Did that surprise you that such a small perturbation would actually result in like an incredible effect?
That's a very good question. I think yes and no. I mean, so we knew that these deep reinforcement learned agents can be very easily fooled. Just given past experience of adversary examples in other domains, we knew that it can be easily fooled. But yes, actually, we didn't expect that it can be so easily fooled. And also, I didn't have time to talk about some more in-depth investigation. I think one thing it really is telling us is that the current deep learning, these neural network architectures, even though they have been making great advances, but really they are not quite learning the right representations. These representations are very brittle. They are really very vulnerable to these type of adversarial attacks and so on. So it just means that there's more work for us to figure out what is actually the right architecture, is the right solutions for us.
And I think that's interesting because it goes back to, we're going to evolve how we account for these things. And the one of the things I liked, Mike, about your data from the Mandiant is that's from incident response. So if you could just speculate a little bit about what incident response is going to look like in a world where we're talking about this. I'm going to come in and I have to figure out, was my model mistrained and not just did someone get into my box?
Well, I think in one of my previous responses, I got away with a security industry trick, which is I said trusted sources. And of course, trust is never binary. How trusted is the source of the data? So incident response for a poisoning attack is going to involve a lot of where did this data come from? How is it influenced? And I think the hard part is going to be the differentiation between intentional malfeasance on training data and accidental. There's this term of art in the security industry, a bug door, which rather than inserting an intentional logical access path, if my username is Bob, let me in, you leave behind a flaw that is plausibly deniable. And that flaw can be exploited by an attacker, even one who left it in. And the problem with bug doors is again, this retroactive assignment of intent. So the really tricky thing about poison data is going to be the differentiation between intentional and accidental malfeasance, and the ability and the tools to prove it.
So going back to my example around Zillow, if I'm controlling the Zillow algorithm and I magically make my house go up by $50,000 this week, your point is that maybe Zillow won't even know it was intentional. Maybe I just tweaked some weight somewhere. Is that what you're saying?
It's going to be very difficult. Even if first you need the tool set to say this is the data that caused the change, and then the second is going to be an attacker created this data and predicted the effect.
And one thing I think is another thing we can learn from the security industry is actually some work that you've done, Taisu, on looking at even supposedly isolated systems like SGX and inferring data about them just from observations.
Right.
I wonder if you could talk a little bit about that.
So when we are chatting with Intel engineer, one interesting thing, one interesting technology called Intel SGX has a great potential to hide. For example, Intel SGX is one of the hardware features that nicely hide your data so that you can do the confidential computation in the cloud. What's interesting thing about this, a lot of industry has a great demand on hiding those data, but they still want to provide these services outside. So for them, now in this current software model, they really consider the data is really important, but at the same time, they want to serve. And somehow, this is contradicting goals. Actually drive a lot of research in security community that, okay, is there any way, side channel, for instance, way to infer those model out of those nicely isolated enclave, for instance. This is one of our work that recently published in using security.
And what was nice about that is it showed, we think this thing is a black box, we think this thing has certain guarantees, and you showed that it actually doesn't.
Right.
So with that, I'd like to move on to what can security learn from AI? And I think we saw some great examples across all three of your talks. So like, what are some ways we can learn from AI and what we're doing? Again, Taisu, I want to start with you and sort of talk about the competition. I mean, both you and Dawn, participate in this DARPA Cyber Grand Challenge. Do we need to have more of those? Is that, the way forward? What do you think?
So okay, this is as a player. So I joined the DARPA CGC quite late because that happened after I joined Georgia Tech. So I don't have permission to start. But we joined about 2 years ago before the final. So I spent a whole lot of time like engineering. But what's interesting outcome of this opportunity is that we thought there should be a lot of breakthrough in program analysis and the way we play the games, and for example, plannings and etc. But at the end of the day, every single player are doing the same. For example, everyone is using AFL, everyone uses some form of the symbolic executions, everyone is G3, the server, but we don't kind of expect, we kind of expect more than this. But at the end, it seems they're competing with the quite similar, they took the quite similar approach that we understand.
Yeah, and Mike, I know you have to leave, so I'll let you sort of field that as well.
Well, that convergence of approach is what we get out of grand challenges. When you say anyone in the world can play, there's no barrier to competition, it's a prototyping challenge. What came out of the DARPA self-driving car challenge is kind of what came out of Cyber Grand challenge, which is we have a kind of a confirmed prototype design for what the state of the art is. And I think for an AI audience, what's amazing about that state of the art is there's both no true, really effective known public application of deep learning yet, and there's a corpus that is mostly unsolved, that's really well groomed of unknown software, very small examples with flaws in them. And that corpus, I think the time to do something like this again is when we move the needle on that corpus from, I think, 20% were solved at the final event to something like 50%, whatever technology causes that jump. And maybe it will be AI. That's probably the trigger to try a competition like this again.
So let me add a little bit about like quantification of the progress. One great outcome of this DARPA CGC in general is a data set. So these days, if you see all the fudging papers and symbolic execution paper, and these are the reference model because we kind of understand all the software stack we already apply. We have a good experience of those software stack. Now, if somebody propose new fudging strategy, then DARPA CGC data set is the reference model that you have to tackle.
I see. Dawn, any thoughts on this?
Yeah, I think also, I guess a little bit back to Tesu's point earlier. I think for these challenges, so first of all, Mike did an amazing job for organizing the challenge. Absolutely. But still, like for every challenge, it has to make certain decisions. Yeah. Because you have to limit the scope, you have to really set the stage. So I think, for example, we had other techniques that just given the requirements of the challenge, we couldn't use them. So I think that's also one of the reasons potentially why different teams also tried similar approaches. But then that also goes back to Tesu's other point earlier about, I think, right, so in machine learning, again, I think there is also a lot of debate about this competition as essentially a marker for progress. On one hand, I think we absolutely should embrace this. I think as human beings, that's we are also social animals in some sense, that actually helps with the community have a clear target to make improvements. But on the other hand, I think maybe more efforts, even more community efforts should actually go into what is actually needed, what would be the best competition to set up, what are the best tasks as a whole community that we should line up. These are the milestones, these are the tasks that we should consider. I mean, similarly, again, Mike did an absolutely amazing, fantastic job organizing the Grand Challenge. And I know personally how much effort he has put in designing these challenges. And I think DARPA has put in a ton of resources in this. But actually, I think going forward, we should consider this as a community effort. So it's not just only on Mike's shoulder. But although not Mike is at Microsoft. So I think these are actually, in some sense, from what we have seen, so these are great drivers for the whole community to make progress. But also we know the risks if we design the wrong tasks. For example, in some, I think, even in Percy's talk earlier, I think yesterday, talking about how data sets can affect, if you just report performance numbers on the data sets, actually you can mislead the community into wrong directions or focus on wrong tasks. A lot of people write about articles, even AlphaGo. It's a great advances, but in terms of making progress, making progress for AI, there are lots of questions there as well. And I think going forward, I actually would love to see as a whole community, we have a bigger community effort so that these such important tasks are not just resting on the shoulder of a few individuals, actually be a much more a community effort, and with the community also putting more resources into it.
All right.
So Don, I have to go. I took my microphone off. Parting thought, CGC was designed to be computers play the game of hackers, and that game, CTF, was kind of designed by the hacker community. So it was an attempt to bring machines into something that people did. But in terms of designing competition or using competition to drive the state of the art in computer security forward or AI forward, I agree completely that there's a whole bunch of work we can do there, and the power of competition is incredible. So I would love to hear, actually, new proposals for how to use competition to accomplish that purpose.
Right.
And I'm going to run.
Yeah, thanks a lot, Mike.
All right. Thanks very much, Mike. And with that, we're going to switch to the last thing, which is what does security look like after AI happens? And the thing I love about both your answers is they're very different. Very, very different, right? I loved the notion of what a new advanced persistent threat is. And then, Dawn, from your talk, I got that advanced persistent threat might be living inside my head. So I guess one thing I find interesting is when we're working on something like this, where it's still a little bit earlier, a little bit ahead of the curve, like the brain-computer interfaces, and I'll start with you, Dawn. How do you think about the limitations that are sort of transient, like today's headsets have certain limitations, but they'll get better, versus limitations that are like really fundamental? Like, how do you think about that when you're framing research in this kind of area?
Very good question. I think, so the important message I really wanted to get through is that I was only using the BCI work that we did as one example. As we move forward already, we can talk about we are in the Internet of Things, and we will have more and more sensors around us, more and more advanced sensors and so on. And essentially, we want the AI to be our assistants, but at the same time, that means that they are going to know more and more about us as well. And then this, of course, on one hand, it facilitates us, but on the other hand, it really opens a bigger attack surface, things that we have not really experienced with in the past, that we have not anticipated in the past, where the attacker could launch completely new types of attacks. And that's just one example how, again, with more and more AI that's permeating or penetrating our daily life, the entire society, there will be new types of attacks that we've never even imagined. And here we're not even talking about AI itself is becoming really intelligent, how AI itself can turn on the human. It's just the attacker could misuse AI to launch new types of attacks.
So I really like that, Dawn, because there was a question at the Harry Shum Fireside Chat around what will the business look like after AI takes off. And so ties to what I love about your advanced persistent threat is, what is the Mandiant of the future, the APT hunter of the future going to look like?
So first of all, the reason that we are speaking a little bit differently is about how you define security in the future. The one thing I was focusing on is about defending the particular company, particular organizations as a defense mechanism. If we apply AI-based approach with our traditional defense mechanism, like intrusion detection system and firewalls, any kind of defense mechanism you can imagine, then a lot of people rely on those mechanisms, and most of them now start working as driven by data. And if those kind of data should be collected somehow, and most of them has a probabilistic meaning, which means if a lot of people start relying on those kind of security mechanisms, it seems like working in normal cases in most of the time. But in terms of APT, advanced persistent threat, so if I start targeting the particular person in the world, so really preventing that is kind of questionable, because we don't know so whether kind of new attempt is really can bypass the machine learning model when we deploy in the real world. So this actually made me a little bit scared about the APT kind of attacks in the future.
All right. Well, we're going to wrap up our discussion there. Just to let everyone know, these are the questions we talked about. And as a next step, if you're in security, reach across the aisle, find an AI person. And if you're in AI, reach across the aisle and find a security person. Because I think we've heard there's a ton of new techniques to apply, lots of great questions, and lots of new things to do. And our panelists will be here for people who want to sort of have some discussion afterwards. And thank you very much for your time. Thank you, everyone.
Thank you.